Section 7.2 is on page 519, talks about trigonometric integrals. So we have integration by the u-sub. That's one technique of integration. We know about integration by parts now. And we have 3 more to go. 7.2 trig integrals, 7.3 trigonometric substitution, and 7.4 partial fraction decomposition. And that's pretty much all the rules we have. So 7.2 is on page 519, talks about the third case, trigonometric integrals, or the third type I should say. Remember that the sine of 2 theta equals twice the sine of theta cosine of theta. It would be very helpful to divide both sides by 2 and use this instead. That saves you a lot of time. This came up before. I wrote it down, then I erased it. I said when we get to chapter 7 I'll talk about it. There it is. We know that cosine of 2 theta happen to have 3 formulas. Cosine squared minus sine squared, twice cosine squared of theta minus 1, and 1 minus twice sine squared of theta. If I solve for sine squared, so if I solve for sine squared, I'll get 1 minus cosine of 2 theta divided by 2. And if I solve for cosine squared, I'll get 1 plus cosine of 2 theta divided by 2. And we know the most famous of them all, Pythagorean identity, sine squared of theta plus cosine squared of theta equal 1. If you divide by sine squared over sine squared is 1. Cosine squared over sine squared is cotangent. 1 over sine squared is cosecant squared. If you go back to the first equation and you divide everything by cosine squared, sine squared over cosine squared is tangent. 1 over cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So, bottom line, we need to know those. And now, if I look at page 524, I'm looking at problem number 8. If I want to integrate, the problem is, if you remember either of those two formulas, you cannot do this problem. The only way, sorry about that, a glitch in the computer. The only way I could integrate an even power of sine or cosine is by using power reduction, no exception. So there's no way around this. When I look at the problem number 8, many integrals you'll have few options, not this one. If I see an even power, it must be the power reduction. Nothing else works. This is 1 minus the cosine of twice the angle divided by 2d theta. The angle being right there. If you double that, that becomes 2 theta over 3. And I'll take the 1/2 out. And the integral of 1 is theta. The integral of sine is the cosine. And as we agreed, if you take a derivative, you multiply by 2/3. If you integrate, you divide by 2/3. And we should know that, or keep in mind that, anytime I divide by a fraction, it's like multiplying by the reciprocal. So that's really 3/2 the cosine of, if I put it in there, 4 pi over 3, minus, if I put a 0, that is 0 minus cosine of 0, and of course it's 3/2. And that would be 1/2 times 2 pi minus 3/2. Cosine of 4 pi over 3, well, pi over 3, that's radical 3 over 2. 4 pi over 3, cosine is negative. Oh yeah. Plus 3/2. I will accept that as an answer on a test. On the homework you clean it up, but on the test that's more than sufficient. If I look at problem number 12, well, I see a perfect squared. That's the integral from 0 to pi over 2. If I FOIL, that's 4 minus 4 the sine of theta plus the sine squared of theta d theta. Well, this is 4 theta, that's not a problem. This is plus 4 the cosine of theta, that's not a problem. And I'll do the evaluation at the end. The problem is with this. You really want to think of this as 1 minus the cosine of twice theta divided by 2. So if you integrate this, you take the 1/2 out. That will be theta minus the sine of 2 theta divided by 2. All evaluated from 0 to pi over 2. That would be 4 times pi over 2 plus 4 times the cosine of pi over 2 plus 1/2 times pi over 2 minus, if you put pi over 2 in there, 2 times pi over 2 is pi, and the sine of pi is 0, minus, putting a 0 in, that's a 0, plus 4 times, cosine of 0 is a 1, plus 1/2 times 0, and if you put a 0 in there, you'll also get a 0. So, again, on a test, I really don't mind you leaving the answer like that, that's not a problem. This is pi over 2 pi plus 0 plus pi over 4 minus 4. So that would be altogether, I could get a whole comment, or I could say that's 4, 8, 9 pi over 4 minus 4, or 9 pi minus 16 all over 4. It makes no difference. That's the same thing. So the strategy for sine and cosine, in this section they deal with sine and cosine and secant and tangent. Strategy for evaluating sine and cosine. If I look at a sine and cosine, and if I notice that one of them is odd, whichever is odd, I save a factor. That will be du. If the sine is odd, then I'll save a sine factor. That will be my du. And do remember the power reduction if they are both even. That's the only way you could do the problem. So looking at the next set of problems, looking at number 2, for example, if I see that a sine or a cosine is odd, then it's a nice integral. I notice that's odd. I'm going to save a sine of theta d theta out. And remember, this is sort of your du. Which means what? I must have a sine squared of theta left times cosine to the 4th of theta. And if this is my du, and now you really start thinking about how this u substitution works, what do you take a derivative of to get sine cosine, of course, which means you need to get rid of this. And what do we know? We know that sine squared is 1 minus the cosine squared of theta. And now if I let u equal cosine of theta, du will be negative sine of theta d theta. So this becomes the integral, and let's color code those. That's my u. And du is right there with one minor exception. And what this will be u to the 4th minus u to the 6th. So this is negative u to the 5th power, u to the 5th power divided by 5 minus u to the 7th power divided by 7 plus c, and that would be negative. And what was u? If you really look at it closely, u was a cosine. So that is the cosine to the 5th of theta over 5 plus the cosine to the 7 of theta over 7 plus c. I don't want to squish things anymore. negative cosine to the fifth over 5 of, oh man, plus cosine to the 7 of theta over 7 plus c. There it is. And if I get to number 4, well, I see a sine to the fifth. That's good. That's odd. Anytime I see a sine or cosine that's odd, I split that up. I'll say sine of x dx. And again, this is going to be my du. What do you take a derivative of? Well, that's going to be sine to the fourth of x. And here I have a couple of options. I could say this is sine squared times sine squared, or I could say that's the sine squared of x squared, which is 1 minus the cosine squared of x squared times sine of x dx. If I let u equal the cosine of x, du is negative the sine of x dx. And that would be a negative the integral. Again, there is my u. And du off with a minus. I already took care of that. And this is 1 minus twice u squared plus u to the fourth. Right? So if I integrate that, that's u minus 2u cubed over 3 plus u to the fifth over 5 plus c with a negative. And that would be negative. U is a cosine of x, it's right there, plus 2/3 cosine cubed of x plus 1/5 cosine to the fifth of x plus c, or negative c is irrelevant. It's the same thing. And if you don't understand that, ask me in class. I'll be more than happy to show you. And I'm looking at problem number 20. Here, I can't seem to integrate that, so I'm going to need integration by parts. I'm going to let u equal x, du is dx, and I'm going to let dv equal the sine cubed of x dx. Now I'm going to shift that a bit to the left, and I'm going to say v would be the integral of that. That's the integral. Take a sine of x out, dx. Oh, they're all happening to be sine, which is no fun. And the sine squared is 1 minus the cosine squared of x. So this, I want v. V will be, here I'm going to let w equal cosine of x. dw is negative sine of x dx. So this becomes the integral of, here, let me keep it standard. V is going to equal, so this is negative the integral of 1 minus u squared du. V is going to equal negative u plus u cubed over 3. And if I put a cosine there, I'll get v to be negative cosine of x plus cosine cubed of x over 3. Alright, now you know what? I'll tell you what. I'm going to move this work above. Missed one. Oh, come on. Okay. Missed one tiny piece. I'm going to move this part. Okay, third time will be a charm. Shrink. Okay, and I'm going to say this is going to be u times v minus the integral of v du. Well, u is right there. And v is right there. So u times v, that's going to be negative x the cosine of x plus x cosine squared of x over cubed of x over 3 minus the integral of v du. That will be negative cosine of x plus cosine cubed of x over 3 dx. And that is going to equal negative x cosine of x plus x cosine cubed of x over 3 minus, and what do you take a derivative of to get a cosine the sine? Minus the integral 1/3, and here I'm going to split the cosine cubed like we just did. I'm going to say that is cosine of x dx, and finally this will be cosine squared, which is 1 minus sine squared of x. I'm going to let w equal sine of x. dw is cosine of x dx. So this integral, this part, that would be the integral of 1 minus u squared du. That would be u of w. I'm so stuck on u. W minus w cubed over 3, right? And w is the sine. So this is going to be the sine of x minus the sine cubed of x over 3 times negative 1/3 negative x cosine of x plus x cosine cubed of x over 3 minus sine of x plus c. Of course, you could combine those and make it a bit nicer, but there it is. Now, the rules for tangent and secant are slightly different. Now, I do provide this formula on your test. Let me just, here we go. For this coming test, this is all you need. So, derivative of inverse sine I provide, cosine I provide, cosecant, secant. I provide this rule, which I'm putting in your notes. The rest will come back later. So this rule right here that you see is actually right there. And this is what it says. It says, if you see a tan and a secant, if tangent is odd, that's all that matters. If tangent is odd, you're going to save secant tangent. By saving a secant tangent, that's your du. What do you take a derivative of to get secant tangent? Secant. Think that way. It'll help you a lot on the long run. And if you see that a secant is even, you would save a secant squared. What do you take a derivative of to get secant squared? Of course, tangent. Now, this is provided. If I see tangent, secant. If tangent is odd, I know what to do. If secant is even, I know what to do. If tangent is odd and secant is even, you could use either of those, makes no difference. If I have secant tangent and the tangent is even and the secant is odd, then this rule doesn't work. Convert everything to sine and cosine and proceed using sine and cosine rules. So if I look at this problem, if they're both even, I know it's going to work for sure. I have this test handy, this table handy, because I already have that formula sheet. You could use that on every test. I'll upload that in Canvas pretty soon. So, I noticed that it's secant even. It says save a secant squared. Save a secant squared of theta d theta. Do remember, this is your du. What does that mean? That means I must have taken a derivative of tangent. So, if I took a secant squared right there, that means I have a secant squared left. And I know that if I'm playing with a secant squared is tangent squared of theta plus 1. And now it's obvious what to do. Let u equal tangent of theta. Du is secant squared of theta d theta. This becomes the integral of tangent is u squared into u squared plus 1. And this is simply du. So this is nothing more than u to the 4th plus u squared. Add 1 to the power, divide by that. Add 1 to the power, divide by that. And if you plug it back in, if you take a derivative of tangent to the 5th of theta plus tangent cubed of theta, that will give you what's up there. Another problem, if I notice they're both odd, that's good news. That means this rule works. And how does that work? Well, if I see that tangent is odd, I'm going to save as secant tangent. What do you take a derivative of to get secant tangent? We take a derivative of secant. So this right here will be secant squared of x, but this will be tangent to the fourth. And I need to get rid of tangent to the fourth because I'm going to let u equal secant. And this is tangent squared squared. This happens most of the time. And if I look at tangent squared and figure out what tangent squared equal, tangent squared is secant squared of x minus 1. And now if I let u equal secant of x, du will be secant of x tan of x dx. You could apply the same rule for cosecant cotangent if you wish, or just change them to sine and cosine. This is my du. This is the integral, and this is my u. So this is u to the fourth minus 2u squared plus 1 times u squared. This is the integral of u to the sixth minus 2u to the fourth plus u squared du. That is u to the 7, but I know what u is. I could start taking a bit of a shortcut and plugging those in. So I could say the answer to this will be secant to the 7 of x over 7 minus twice secant to the fifth of x over 5 plus secant cubed of x over 3 plus c would be my answer. And if I'm looking at number 16 and I notice that this is even and that's odd. Oh, actually, I'm sorry, that's not even a secant. I could play with this and manipulate it if I want. That is, I could say, well, I could go for secant tangent. I could go for, you know what, if it's not secant tangent, I like sine and cosine. This is sine squared of x over cosine squared of x times cosine cubed of x dx. This cancels two of those. The integral of sine squared of x cosine of x dx, well, guess what? If I'm thinking of this as du, what do you let u equal? Sine of x. Du is cosine of x dx. So this becomes the integral of, that's my u squared, and that's my du. So that will be u cubed. U was the sine, u cubed over 3. There it is. That'll take care of business. Now I do want to derive. I said I need you to memorize 4 integrals for me. We already have 2. This is the third. Somebody thought of this. Now I'm not assuming you're going to think of this, but look at what somebody thought. If you put 1 over cosine, it's a troubling. It doesn't work. Somebody decided to multiply by 1. What's their 1? It's secant of x plus tan of x over secant of x plus tan of x. That's 1. As long as secant of x doesn't equal tan of x, this would be the integral of secant squared of x plus secant of x tan of x over secant of x plus tan of x dx. And they used a u sub. They said, let u equal the denominator. Then du will be derivative of secant is secant of x tan of x. Derivative of tangent is secant squared of x dx. And magically, again, don't ask me how they figured that out. If you let this be your denominator, then guess what? That's your du. That simple. Again, how did they think of that trick? Beats me, but hey, Isn't this natural log of absolute value of u plus c? And what's u? So, up till now, I need you to memorize that the integral of secant of x is natural log of secant of x plus tan of x. The integral of tangent of x, I derived that for you. Let me derive it again. If I let u equal cosine of x, du is negative sine of x dx. This becomes negative the integral. That's my u. And that is my du. That is negative natural log of absolute value of u, and u is the cosine of x. This is fine. In this book, they make that a power, and they say that is natural log 1 over cosine of secant of x plus c. Either of those will do. This book sticks with this. Other books I've seen use this all the time. Why are there two pluses? So there's your second. And this one I derived for you. Also, if you look at if you look at the integral of cosecant of x dx, that turns out to be almost identical, except it's a minus. But those are the three that I need you to know for now. And if I'm glancing at page 523, example 8 in the book, look at this problem. The integral of secant cubed of x, I keep that away from your test. And if this on your test, you could leave it like that for my class, out of mind. And a tricky problem comes up every now and then. What do you take a derivative of to get tangent squared? That's a bit tricky for students. It turns out it's troubling because there's only one way of doing this problem. If you remember the identity that this is secant squared of x minus 1 dx, you're in big trouble. What do you take a derivative of to get secant squared? The tangent of x. What do you take a derivative of to get negative 1x plus c? And that pretty much seals this problem, this section. 1 through 43, every other odd is sufficient. 55 and 65. If you do those and you're still hazy about them, then you do the odds.